Hello, my name is Luis Perez. Welcome to my charged tapes experiment report. The purpose of this lab is to observe how two charged pieces of tape interact and use physics and build a computational model to estimate the charge on each tape. We'll use Newton's second law, gravity, and Coulomb's law to describe the forces acting on the tapes. My main result is that each tape carried about 26.6 nanocoulombs of charge. The experiment setup. I cut two clear strips of tape, each 30 centimeters long. Clear tape has a mass density of about 1 gram per meter, so each strip had a mass of about 0.0030 kilograms. When I prepared the U-shaped tapes, I suspended one above the other. The top tape floated about 5 centimeters above the bottom one. The gravitational force acting on the tape force on the floating tape is its weight. So it'll be F. So the force of gravity equals mg, which is 0.003 times 9.81, which will equal 2.94 times 10 to the negative third newtons. Now at equilibrium, the upper electric repulsion equals the downward gravitational force. So the electrical force is going to be equal to the force of the gravity, which once again is 2.94 times 10 to the negative third newtons. This balance is what's caused the tape to float. To model this, I treated each tape as a single point charge at its center. Coulomb's law tells us that the force between 2 point charges is F equals K times Q1 times Q2 divided by R squared. Since both tapes carry the same charge Q, it simplifies to the force is equal to K Q squared divided by R squared. This is the equation I used to solve for my Q. Now, in my web glow script program, I set the initial conditions to, well, the tape length was 0.3 meters. The tape mass was 0.0003 kilograms. The separation between those two was 0.05 meters. Gravity, obviously 9.81 meters per second over meters per second squared. And K equals 9 times 10 to the ninth. I wrote a function called E field that calculates the electric field vector at any observation location. It uses the relative position vector, its magnitude, the unit vector, and Coulomb's law. Then I assigned equal charges to two of the centers and calculated the electric field at the top of the tape using the bottom one. Finally, I calculated the force on top of the tape using force equals to the uh, the charge times the electric field at that point. My program prints both the electric force and gravitational force to check if they are balanced. Now, well, once the program is ran, it shows that the electrical force is 2.94 times 10 to the negative 3 newtons, and the gravitational is also 2.94 times 10 to the negative 3 newtons, which confirms the equilibrium condition. The program also spits out the required charge per tape, which is 2.6 times 10 to the negative 8 coulombs, or about 28.6 nanocoulombs. In the visualization, you can see to your left, the green and blue boxes represent the two tapes respectively. The red there should we can't see in this position, but there will be red spheres where the tips of the purple and blue arrow are pointing. The orange vector arrow represents the electric field. The purple electric arrow represents the electric force on top of the tape, and the blue the blue arrow represents gravity or the weight pulling down. At the flowing condition, the purple and blue arrows are opposite, showing the balance of forces. So the force of the electric and the force of gravity. Some assumptions and errors I did to simplify some assumptions I did to make this more simple was ignore air resistance, treat tape as a point charge while it's obviously an object with a bunch of charges spread out through the entire piece of tape. And we also assumed that there was equal amount of charge on both tapes. Possible errors include include non-uniform distribution of charge on the tapes, external objects acting on the field, or charge leakage between the touch of the tapes when I was setting up the experiment. We have a couple what if questions. If the electrons had a positive charge and the protons a negative charge, nothing about the observations would change. Like charges would still repel and opposite charges would still attract. Only the labels would be reversed. And it's important to handle the tapes with as little uh, as little possible contact with hands or other surfaces because the charge leaks away, reducing the overall repulsion effect. In conclusion, I observed one tape floating 5 centimeters above the other due to the balance between them between gravity and electrostatic repulsion. My computational model used Coulomb's law and the glow script estimated each tape carried about 28.6 nanocoulombs of charge. This lab shows how combining experiment with models lets us measure and understand invisible quantities like electric charge. Thank you for watching.